Last time we started with ultrasound and talked about ultrasound physics, covering the main idea regarding ultrasound imaging and the concept of ultrasound transmission. We discussed how you receive the ultrasound pulse after it interacts with the various elements inside the patient's body, and how this is then translated into a signal that can be hyperechoic, hypoechoic, or anechoic. We talked about the difference between sound waves and X-rays, highlighting the clear distinctions between them, such as which wave is longitudinal, which is transverse, which requires a medium, and which does not. We also discussed which has a constant velocity and which has a variable velocity depending on the medium, illustrating the difference between transverse and longitudinal waves, as well as electromagnetic waves like X-rays. The presence of an electric field and magnetic field affects the direction of propagation. We discussed sound waves, which are considered longitudinal waves, and their movement direction is parallel to the direction of wave propagation. We talked about ultrasound waves, which are above 2 million hertz in terms of frequency. We covered the production of sound, the concept of the tuning fork, the movement of molecules, and the compression process that occurs in molecules, as well as the refractions and how the wave shape appears, or how the sine wave representing ultrasound looks. We discussed our transducer or probe, the piezoelectric materials, such as the existing draconite or crystal, and the concept of compression that occurs in it, or the change in thickness due to exposure to external pressure, which starts to alter the technology of the transducer. Consequently, the transducer produces pulses that vary in frequency. We also talked about the topic of the transducer and the technology and why the transducer or the crystal technology is chosen. The wavelength that I want to work on for the topic of resonance and to produce a wave that is entirely in M phase without experiencing destructive interference. I mentioned that the more I adjust my thickness, the pulse I get will have a high frequency and a short pulse length. The result, of course, is that my wavelength is short, unlike using a thick transducer or thick crystal, which will give me a long pulse length and a low frequency crystal. It will give me a long bulk length and a low frequency. We talked about the relationship between thickness and the relationship between frequency. If I want to work on reducing the thickness, in this case, I will increase the frequency. Consequently, the wavelength decreases. The mechanism is achieved by changing the applied electric field on my crystal and altering the diable orientation, which preserves the change in the crystal's technique. This gives you your ultrasound pulse. We also discussed the backing block or damping material located on the backside of the piezoelectric material and its role in the damping process, which helps to control your pulse. We said that we can adjust if I want to, depending on what will happen, whether it is in this form or if you are synchronizing it as if you are representing it, as we previously mentioned. You can keep this working for a long time, which means you can operate the long-ranging pulse in this case, making the pulse duration large or the pulse length long in various scenarios and situations. However, this comes at the cost of operating at low frequency, unlike when you are doing heavy damping and low Q, which allows you to have high frequency, but results in a short pulse length in different contexts and conditions. As we discussed last time, we talked about the difference between these two spectrums and the factors that affect beam shape, as we have discussed in our previous discussions and elaborations. We also discussed the near field and the differences and parameters that affect it, such as frequency and diameter, along with other parameters that influence it in detail and extensively. The text discusses the transducer and when the divergence angle increases or decreases, as we previously estimated with examples of different frequencies, with different sizes of transducers and their effect on divergence or the dispersion that occurs and their impact on the near field. We talked about the idea of the beam shape that comes out, and the implications of it, of course, we thoroughly discussed it last time, and why I have the area that is particularly relevant to me, because this is the area where what happens is called the near field. There is a certain distance before and after this area, and this distance is where it is highest for me in detail to my work. The conclusion is that there is a process that occurs between what is present and what is emitted, which continues until it reaches a certain area that is significant for you. We talked about the ultrasound concepts regarding pulse duration, pulse repetition period, and there is something called duty factor. The duty factor is the relationship between two things: pulse duration and pulse repetition period. If you set the pulse and period to be the same as the pulse repetition period, then in this case, what you are doing is that the time of the pulse itself is equal to the time of the pulse, which means that in this case, your duty factor will be approximately 1. And in this case, it's as if you are emitting a continuous beam. However, normally, since you are working, your duty factor will be low because the pulse period itself will be less than the pulse repetition period, as there needs to be space to receive the signal that comes back from the differentiation present. We talked about depth calculations and how to determine the depth or the location from which the signal or your pulse is coming, of course, through the equation of time flow, and we linked it to the pulse repetition frequency last time. We talked about the meaning of the word, and we said that it represents the amount of what happened. We mentioned that approximately about nearly roughly 11% of what always occurs is a result of the interactions, interplays, exchanges, communications between different tissues, various tissues, diverse tissues, distinct tissues. If the different tissues are 100, then part of them will experience results from the interactions, interplays, exchanges, communication between them and what is present, for example, in the liver. This leads to isotropic scattering, uniform scattering, even scattering, consistent scattering, which causes a loss of part of its intensity, strength, power, force. Some of it is lost as heat, and there is a part that transforms, changes, converts, alters into other forms. All of this affects, influences, impacts, modifies the signal itself. If you want to know the target, objective, goal, aim that occurred from the equations, formulas, calculations, computations, it states, declares, asserts, proclaims that the target, objective, goal, aim that occurred is 10 log, logarithm, logarithmic value, logarithmic function. In what happened in the year, forget about the one who says that the reflection loss or the dB loss that occurred is a logarithm. If you want to know, the part that goes back to the transducer regarding the incident wave that originally came from the transducer here represents the description in intensity, and since intensity is considered to be approximately equal to amplitude loss, means that I have a signal loss in amplitude. It's like multiplying a value of 20 by 20. And the same equation applies to you. If you want to understand the loss in amplitude, it means I have the signal. In this context, what happened is that when attenuation occurred, the amplitude started to decrease. The amplitude, of course, refers to the peak, which is the height of the peak itself. The loss that occurred in the amplitude means a loss in its intensity. If you want to know the loss in intensity, you can use the equation 20 log I reflected, I incident. Okay? So the reduction in decibels represents how much attenuation has occurred, how much intensity has been lost in the beam that is already produced by the transducer. We mentioned that it takes values like -1 decibel or -2 decibels because there has been a loss in intensity. The negative values represent that there is a loss that has occurred. This is the meaning of the term decibel. So if I say 2 decibels, that means 22% loss. 3 decibels, means a loss of about 30% of the intensity that has occurred. We also briefly talked about the interactions that take place. We talked about how I have this idea that what happens to me is based on two things: the density of the medium and the speed in that medium, in my opinion and understanding. For example, if there is something moving between these two, it could be soft tissue or air or whatever the touches are as I perceive it in various scenarios. The reflection that will occur in intensity depends on the difference in acoustic impedance of those touches, such as in different contexts and situations. The greater the difference, the higher the reflection or reflected intensity will be, while the transmitted intensity will be very low, as an example in terms of acoustic properties and characteristics. This even affects us in terms of artifacts like acoustic shadowing and acoustic enhancement in relation to the context of intensity and reflection. For instance, if you have a stone in the skin, you might find that the signal passing through that stone is very low, and consequently the signal that represents anything behind the stone will be weak. Or conversely, it could be in terms of transmission and absorption, in terms of artifacts such as shadowing and enhancement, in terms of signal and representation, in terms of strength and weakness, in terms of stones and skin, in terms of passage and obstruction, in terms of signals and their effects. The attenuating material or object can be neither stone nor bone, or the low attenuating material in this case can cause the reflected signal to not experience significant attenuation, resulting in a hypersignal, which is called acoustic enhancement or acoustic shadowing, as I will discuss regarding the ultrasound artifact. However, the topic of reflection depends on the difference in acoustic impedance between the two media. Here we are at acoustic impedance through this very first equation regarding density and stiffness of materials in relation to sound waves, specifically ultrasound in a given medium. Herein lies where you will find the highest possible level of impedance within bone structures. As I was previously mentioning earlier on this topic, what happens with regard to reflection coefficient? If I want to determine precisely how much treatment or therapeutic process I've reached through using our specific equation Z2 Z1 over Z1 plus Z2, which is indeed an essential equation existing for each type of tissue or medium, then if I wish also calculate transmittance ratio along with simplicity area considerations involved here, it would be expressed as 1 minus reflection value. In such cases like these ones mentioned above, you can subtract from totality, which equals 100%. For instance, example-wise speaking, hypothetically now, if we say assume that your calculated reflection ratio stands at 50%, then logically following deduction means transmittance for yourself would equally stand around 50% too, thus representing other half remaining. For example, if you have an interface between soft tissue and soft tissue, the reflection is about 0.01 to 0.02. So the transmission is the remainder to 1, which means you are left with 100%. If you multiply the reflection value of 0.01 by 100, you get approximately 1%, which means the reflection is between 1% and 2%. If the reflection is between 1% and 2%, then the transmission is between 98% and 99%. If I have an interface between soft tissue and bone, the reflection is 40%, while the transmission is 60%, and the amount that returns to the transducer is 40%. Now, what is the highest value you have for soft tissue and air? Reflection is at 99% and transmission is just 4.1%. That's why, for example, when you use a transducer on a patient's body, you apply gel. Why do we use this gel? To reduce the impedance present between the crystal itself and the air, because there is air present here. This air can cause significant reflection. For the second transducer, which prevents the beam from penetrating and entering the soft tissue, therefore the presence of this gel reduces the impedance present, which is very important. The topic of impedance is crucial, especially when we talk about the backing block material that provides damping. We mentioned that the backing block material has the same impedance. Why the same impedance? Because if there is something reflected or something that returns from the crystal and goes in that direction, it does not experience reflection. This is because if the impedance of the backing block material is different, the backing block material will be different. It will reflect back again and return again to the crystal. I don't want that. I want it to disappear because I only want the ultrasound that came from the crystal and went into the skin. We mentioned, of course, that I also have other types of interactions. Besides reflection, I said that if I have, for example, things like hepatocytes that are present or the cells that are in the patient, their size is smaller than the wavelength of the ultrasound. In this case, isotropic scattering occurs, which is responsible for the echo textures of the liver in ultrasound. We talked about this in detail. Here, there is indeed a part related to echo texture, which is actually a result of isotropic scattering. It entails small particles compared to the wavelength of the ultrasound. This shape actually includes a part like the diaphragm, which is a smooth reflector called a mole, bright signal, or hyperechoic signal. This occurs because it is a strong interface resulting in very high performance. There is also a part where if this surface is not very textured, it behaves in a certain way, which does not contribute to the intensity of the signal. Therefore, the signal appears in a certain way, and the image, as we see, does not remain smooth or does not take the same characteristics as the liver area. So, if I am dealing with smooth areas, then you have nominal thinking refers to diffuse reflection when dealing with certain surfaces, when dealing with small size particles. Scattering or isotropic scattering occurs, which involves small interfaces or small sizes that are less than the wavelengths of the ultrasound pulse. Additionally, we also discussed refraction. In addition to what has already been mentioned, it is important to highlight that there is indeed a significant presence of the same element repeatedly occurring in the context we are discussing. The topic of refractive reflection, I said that if I have an incident wave like this and it strikes the interface between two media, refraction will occur. It is supposed to continue in this path, but it takes another angle or it takes a different angle, and this is governed by the angle at which reflections occur according to Snell's law, which relates the angle to the speed in the media. If I move from a medium with speed c1, where c1 is less than c2, the speed of the second medium, for example, the angle increases because it moves away from the normal. What is the normal? It is the dashed line that is perpendicular to the interface. It moves away from it, so your angle increases. But if it moves from a medium with a higher speed to one with a lower speed, the refraction angle decreases, bringing it closer to the normal, which is the perpendicular line at the interface between the two media. These are the topics that represent two of the angles present, the incident angle and the refraction angle, and the phenomena associated with them. This subject is very important in the artifacts that appear and what happens, e.g., if the probe expects the signal, which is the reflected one, is coming in a straight line. So now the beam that is the incident one is here, and when refraction occurs, this beam falls on an object present at this location. If this signal reaches the transducer, it considers it came as if it were in a straight line. It sent it at a certain angle or in a certain way. Therefore, the incoming signal, when it comes to location, is placed in the wrong location. It is preferable, for instance, during the imaging process, that the angle of the transducer with the patient's body remains normal. In such cases, you might find yourself taking images from different angles or different views. Make sure of the location of the lesion or object in this position, or whether it has changed. Different angles or different views help you avoid the artifacts that may appear in this case due to the mispositioning of the object. Attenuation, as we said, is measured in decibels per centimeter per megahertz, meaning that for each frequency of 1 megahertz, a distance of 1 centimeter results in a certain amount of loss or attenuation. For bone, of course, one of the highest values is 22 decibels per centimeter per megahertz. So the loss I mentioned due to attenuation is very high in bone compared to other tissues. As we mentioned before, attenuation depends on frequency, depth, and the attenuation coefficient. The attenuation coefficient is related to the tissues or materials, and the frequency is related to the ultrasound pulse. The higher the frequency of the ultrasound pulse, the higher the probability of interactions with the tissues and cells present, leading to a higher loss in its energy or intensity. This increases the amount of attenuation as you move a greater distance or to a higher depth in the patient. The rate of attenuation increases and the loss in the intensity of ultrasound pain increases. So now, based on what I have said, I briefly explained and quickly went over the discussion. Now I have a problem. What is the problem? It is that from the discussion we had, we said that if I have high frequency, this high frequency will give me something called short pulse length. What does short pulse length mean? As we discussed before, what are you buying? Hello everyone. I have two important things to discuss. First, the frequency I am working with is a very important parameter in resolution. Right now, I have two objects inside the patient or inside the organ I am imaging. These objects could be positioned one behind the other, meaning they are on the same line. Then, I have two other objects that are next to each other. Now, I want to differentiate between the objects that are behind each other. How can I do that? The idea is that if I have an ultrasound pulse here, it will reflect off the first object, and the transducer will record it. However, part of the wave passes through the first object and goes to the object behind it. The object behind will also reflect part of the wave, so I end up with two reflected waves, one coming from the square and one coming from the triangle. If the signals coming from the square and the triangle arrive at two different times, I can perform discrimination and see if they are different signals or not, and whether I can see the two objects or not. However, if both reflected signals or reflected intensities coming from the triangle and the reflected wave coming from the square arrive at the same time, then they will undergo superimposition or interference. In this case, I won't be able to see them. I will detect them as one signal, and I won't be able to differentiate between them. The second object for me is a bit difficult to see. I can't separate them from each other, so I call this poor axial resolution. If I can see them, then that's good axial resolution. What gives me good resolution in the image is what allows these two pulses to be seen discriminated or resolved well, or not resolved well. The frequency, when I talk about high frequency, it means my pulse length is short. When I talk about low frequency, it means my pulse length is long, as we discussed last time. If I say that my pulse length is short, what does that mean? It means that the number of cycles, or the wavelength is short, meaning the pulse itself is short. Now imagine with me that I have given a pulse here. This pulse has reflected from the first interface or the first object and returned. There is a part that reached the second reflector and I returned. Focus with me like this. If the distance between the two is the second, and if this distance is large, I don't have a bigger problem. If this distance is larger, 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 and this distance is 2 millimeters, then for me, this signal will go and come back. It returned, for example, here it took 1 millimeter, and it returned taking another 1 millimeter. This is because the distance is large. Let's say, for example, we clarify this. This is the pulse length, and these are the two objects, and this is the separation between the two objects, and this is the pulse that I sent, like this. Okay. And here is what is between this one and what I sent. Right. Okay. What if this one?